We have about 20 people right now, so we'll just wait another few minutes. Okay, so I think the attendance is starting to steady out. So let's begin. All right, everybody, welcome to today's Polariton Chemistry webinar featuring Professor Christophe Galland. Before we get started, let me make a few announcements. So here's the schedule of upcoming talks. So after today's talk, we will have 2 more regular talks, right? And then we'll have a special event. This is a roundtable discussion focused on ground state vibropolaritonic chemistry. More details are coming soon. And remember, before each talk, please register at this link. And this is a different link than before, and we'll be using this link for all the future talks. All right. So remember, we have a Polariton Chemistry online community. This is a public Facebook group where new papers, job postings, and other news related to Polariton chemistry can be posted here. So if you haven't joined, please do so. Also, we have a Polariton Chemistry Webinars YouTube channel where we post the recordings of previous webinars. So if you can't make it or would like to rewatch a webinar, you may visit here. Please subscribe if you haven't done so. Now I will go over the mechanics of the webinar. On the bottom of your screen, you have 3 options: chat, raise hand, Q&A. Throughout the talk, if you have any questions, click raise hand. At an appropriate time, I'll ask the speaker to pause. I'll unmute you and I'll let you ask your question. During the talk, if you want to have some discussions with the fellow audience members, you can type it in to the chat. You can also put your questions there. finally, there's the Q&A options. There, you can put any questions, and at the end, we will allow the speaker to answer those questions. And if we don't have time to get to those questions, we can send the questions to the speaker, and the speaker will then answer on their own time, and then we will post the answer to the questions in the comment section of the YouTube channel. Oh, sorry, the YouTube video for this webinar. All right. With that, I will now introduce today's speaker, Professor Christophe Galland from EPFL. So after his post-secondary studies at École Polytechnique Paris, he did his master's and PhD at ETH Zurich in the group of Professor Atak Imamoglu, where he studied relaxation dynamics and photon statistics in single-wall carbon nanotubes and proposed a fully optical method to manipulate electron spins in this material. Afterwards, he did postdoctoral research at Los Alamos National Laboratory in the US in the group of Viktor Klimov, where he did some seminal works revealing various types of photoluminescence blinking in single nanocrystal quantum dots and elucidated the mechanisms associated with each type of blinking. Then he did research at the University of Delaware in the group of Michael Hochberg, where he studied integrated quantum optics and silicon waveguides and other photonic architectures. Then he moved back to Europe, specifically to EPFL under a Swiss fellowship, the Ambition Fellowship, where he studied with Professor Tobias Kippenberg, doing quantum optomechanics. Specifically, he developed theory of molecular optomechanics to explain surface-enhanced Raman scattering. Since 2017, he has been a professor at EPFL, leading the Laboratory of Quantum and Nano-Optics. His group studies single photon phenomena in quantum dynamics and molecular vibrations in plasmonic nanocavities. Without further ado, I will give the screen to Professor Galland, who will be talking about quantum correlations between light and molecular vibrations. Professor, you may now share your screen.
Yes, thank you so much. So I will just share. I hope everything will work smoothly. So yes, you should see the screen and also maybe the mouse.
Yeah,
excellent. Right. Yeah, thank you so much for the very kind introduction and very well documented. So I'm very, very happy and honored to have the opportunity to present at this webinar series. So first I'd like to say that I'm not doing polariton chemistry per se, so I hope that this presentation will maybe give you some some kind of outlook or some new perspective on vibrational dynamics and also plasmonic nanocavities that are closely related to the topic of polariton and polariton chemistry. So I'd like to just start by acknowledging the group for all these people who are actually doing the research, and just a quick introduction. So the work that I will show first in the first part is mainly the work from Santiago and Anna, and the rest of the team. So I will show maybe in the next slide. I will come back to that. The rest of the team is working on two different topics. So we have this activity on probing and engineering light vibration entanglement, which is closely related to also the part 2 of my talk today, which is the study of molecular vibrations inside plasmonic nanocavities. And we also have more recently started some research on quantum sensing using NV centers, and we want to apply this to biological sensing, but also to let's say nanoscale thermometry, in particular in low dimensional materials. So I will go back one step in my slide because I know that the audience is scattered around the world, so you may not know where is EPFL, and just to give you a glimpse of where we are quite close to France and Italy, at the southwest corner of Switzerland. and next to the Lake Geneva. So you can see the Mont Blanc on the other side of the lake, and this is our campus, which is pretty nicely located, I would say. So yes, coming back to the science, I will actually cover 2 topics today, which I will try to not to be too slow on part 1, but nevertheless, I mean, part 2 is much shorter, so feel free to interrupt me. I think it's more important that I can answer your question, and we'll see how far we can go. So what I want to present first is some work that we did using ultra-fast spectroscopy and single photon counting to reveal quantum characteristic of molecular vibrations and their entanglement with light that is spontaneously created during Raman scattering. And in part 2, I will just give a glimpse on our activity in plasmonic nanocavities, and in particular, I'll focus on a phenomenon that we recently discovered, which is a blinking of the luminescence that is coming from the metal itself. So it's pointing to some kind of atomic scale dynamics that is driven by light, and that is actually distinct from the molecular signature for which these structures are built in the first place. And just a couple of words of why I am personally interested in what I call molecular oscillators, which is just a fancy word to say, you know, vibrational degrees of freedom of molecule. So they are, I think, a very interesting route for some application in quantum science and technology for the several facts. So one of them is that because of their high frequency, they can retain their quantum coherence at room temperature, as you will see next. And also they have thereby by nature a very, very high bandwidth, so you can do very fast information processing in principle if you can control these molecular vibrations at the quantum level. And ultimately, they can also be scaled down to the level of a single molecule, which could lead to extremely small device. And this also is a motivation for molecular electronics and other related technologies. And another topic of interest to me is more generally the light-matter interaction. Sorry, I have a typo here, in nanocavities. And here, this maybe also joins better the topic of the webinar series. Can we modify dynamics of quantum systems and molecules in the presence of a cavity with light, or maybe also without light, as is mostly the topic of polaritons, but also more generally trying to you know, make an impact in the field of nanophotonics and molecular science by better understanding these nanostructures. So let me start with the first part. So I want here to convey our work and the conclusion of this work regarding the quantum state and quantum dynamics of collective molecular oscillators or molecular vibrations. And first of all, I'd like to mention that most of our experiments have been done on a crystal. So these are not, let's say, molecules per se. So this is a crystal of diamond, but diamond has 2 atoms per unit cell. And as you may know, in this case, you have a branch of optical phonons, or at least several branches of optical phonons, which, to a very good approximation, behave as a diatomic molecule. So the interaction between unit cell is relatively small, which gives rise also to the fact that you have a very flat dispersion around the gamma point for this optical phonon branch. So we can use this as a model system of, let's say, frozen molecules, if you want, with a vibrational dynamics and a Raman scattering signal that is very much similar to the one of real molecules, if you want. So that's what we will use in most of this part. And I will show you right at the end of this part 1 that the technique is also working for molecules. I will show you the example of carbon disulfide, We have tested it on several molecules, and it's also working, but there is additional difficulties. So in diamond, this vibrational mode that we are addressing has an eigenfrequency of 40 terahertz, which means that at room temperature, if you look at the thermal occupancy of this mode, it's extremely small. It's on the order of 10 to the minus 3. So it's an ideal test bed for ideas or for testing ideas and protocols inspired by quantum optomechanics. So we have an oscillator which interacts with light, which is in a quantum close to the quantum ground state. But we have this difficulty that we are not addressing a single diatomic oscillator. We are addressing billions of them. And the question is, how can we address a single mode so that the picture that I draw on the right is valid? Because this picture is this parabola is the approximation of a harmonic oscillator, but it's valid if there is a single vibrational mode. Once you have many, you would have many such oscillators, and dynamics is more complex. So we have to address a single collective mode, and this is done by controlling two aspects. We have to control the temporal coherence, so we have to use very short pulses, so typically on the order of 1 or 200 femtosecond. And the requirement is that the pulse duration is much shorter than the coherence time of this vibrational mode. In this case, Raman scattering will occur in a regime where the Stokes and anti-Stokes photon are effectively in a single temporal mode. So this is the first requirement. And the second requirement is to control the spatial degree of freedom. So we have to address a single spatial mode, and this we do by imaging the signal that we get from the diamond into a single mode fiber, so that we effectively address a single spatial temporal mode. And the interaction of light now with this collective molecular vibration will be determined by Raman scattering. So I don't go back to the basics of Raman scattering. You probably all more or less know what it is. But in the end, the Hamiltonian of Raman scattering, at least to lowest order, consists of two main terms, which are describing on one hand the Stokes scattering. So you see that this operator AS and B, or AS and B, they create a photon in the Stokes mode, and B is creating a collective vibration. And A anti-Stokes is creating an anti-Stokes photon, A dagger. So this first term is corresponding to the two-mode squeezing, or at least this form is equivalent to what in quantum optics is called two-mode squeezing. So if you want, the Stokes scattering is equivalent to a two-mode squeezing interaction, which is the same as what you have in parametric non-conversion. So it will create perfectly correlated pairs, or let's say twin states between a Stokes photon and a phonon, which is then staying inside the crystal. And the beam splitter Hamiltonian, which corresponds to anti-Stokes Raman scattering, is a state swapping Hamiltonian. So so in this picture, my gray arrow is always the pump. So the pump will be treated, it's treated in this Hamiltonian as a classical field. So it's entering this coupling rate G. And this pump will control the strength of this interaction. And the anti-Stokes interaction can be used to read out the state of the photon, of the vibration. So if you have a phonon inside the crystal, you can convert it with some efficiency into an anti-Stokes photon. So that's the two processes we will use to prepare and read out the state of the vibration. Okay, so the setup we use is schematically pictured here. So we send our ultra-fast pulses with a controlled delay, and we use two different colors for technical reasons that will become obvious. So we have two pulses here. One is at 815 nanometer or so, and the other one is at 700. And we use one pulse, which we call the right pulse, to creates a vibration using Stokes scattering. So it's a probabilistic process. So we send pulse, and once in a while there is a pair of one Stokes photon and one vibration being created. So we collect this signal, filter the laser out, and collect them into the single mode fiber. Once we have done that, we separate the Stokes signal created by the first pulse from the anti-Stokes signal created by the second pulse, which we call the read pulse, using a dichroic mirror with a tunable cutoff. And then we filter further with bandpass these two signals to really get rid of any residual photons from the lasers or the background in order to perform single photon counting. So we use two sets of Hanbury, Brown, and Twiss setup, consisting of beam splitter and single photon detector. And with that, we can then collect all these signals and do analysis of two-fold, three-fold, four-fold coincidence as we desire. Okay, so that's a setup. Now I will try to. So typically, when I have some maybe more interactive setting, I like to ask some questions and have you guess what will be the result. But I will still do it and just have you think about it. So the first question is about the statistics of the Stokes field. So now I'll go back to very basic properties or very basic things in quantum optics. So maybe if you are familiar with the general field of quantum optics, these things will be obvious. But nevertheless, it's the first time that this is measured on Raman signal induced by vibrational modes. So as far as I know, it's never been done before, although it's relatively, the physics of it is relatively simple. So the first thing we can do using the settings that I have shown you, the setup I shown you before, is to focus here on either the Stokes or the anti-Stokes field and measuring the photon statistics using this setting. So you're measuring a G2, a second order correlation function. So in this case, we don't need the two pulses. We can just send one pulse and look at one field. So the first thing we do is we send just the first pulse, which I call the right pulse, and we look at the Stokes signal. So the state after this interaction, if you remember, quantum optics or standard quantum optics lecture, if you apply a two-mode squeezing Hamiltonian for a given time, you will end up with a two-mode squeeze state, which is, the name of this Hamiltonian comes from that, which is a coherent superposition of many, let's say, a series of twin field states. So you have the vacuum state, you have one component with one Stokes photon and one phonon, and then higher order terms, but always coming in pairs. So it's obvious from this Hamiltonian. Now, if you only measure the Stokes field, so you have this this experiment that we do, and you don't measure the vibration because it stays in your crystal and it decays in the environment. In this case, the question I ask you, and you can think about it for a few seconds, is what is the value? So here, what I measure is a G2, so it's a normalized autocorrelation function. So it has a form of something like A dagger AA divided by the square of A dagger A. So this is something you use to characterize the statistics of a field. So if you have a coherent state, it's 1. If you have a thermal state, it's 2. If you have a single photon state, it's 0. So here the question is, what do you see? So you excite this with a laser, you have spontaneous Raman scattering, and you look at the Stokes field. So since you cannot just give your reply on the chat, maybe you can. So you can contribute, but I'll give you the answer, and you might have found it. So you find the thermal statistics, and the reason is that when you do that, you have to trace out the vibrational mode from this wave function, which is a two-mode wave function. And if you trace this out, you will end up with a statistical mixture which is exactly, which has this coefficient 1 p squared. So it's exactly a thermal state with an effective temperature that depends on the value of p, which itself depends on the strength of the interaction and the duration. So basically on the Raman cross-section and the laser power. And we find these statistics. So we find the thermal statistics of this, or pseudo-thermal statistics of this state. And interestingly, it's not only just fun to see that, but it's also important because it tells us that we are successfully isolating a single spatial temporal mode of the phonon, and thereby also of both the Stokes field and the vibrational mode. So the reason is that if you have several, if your detector is collecting light from several modes of, which are all in a thermal state, the G2 you can compute, it will decrease with 1 + 1 over n. So only if n equal 1, you can really see the G2 of 2, which is a bunch statistics of light, which is what we find. Now we can use the second part of the setup to measure the same thing on the anti-Stokes. So the experiment is similar. So we send just one pulse. And we see what is the statistics of the anti-Stokes field. So remember, if I do that, what I will be doing is converting whatever vibration is inside my crystal into a Stokes photon, into an anti-Stokes photon. But I told you that my vibration in the first place should be almost in the ground state. So then I also ask you the question, what do you expect if I measure the statistics, photon statistics of something that was in the first place very much close to the ground state? So here again, I'll give you the answer before you, since you cannot really interact in these settings. So the answer is that you also see thermal statistics, because although it looks like being in the ground state, it's nevertheless a thermal state. It's just the crystal is at equilibrium at room temperature. It has very small probability of being excited, but this finite probability is still following a thermal statistics. So you will find some probability to have a first excited state, and then an even smaller probability to have a higher excited state. And these things shows a bunch statistic, this distribution, according to the same argument as a previous case, but for a different from a different origin. So here it's truly a thermal state in thermal equilibrium. Good. So I'm not sure if there is
Professor?
a question. Yeah.
Yeah, actually there is a question.
Yeah.
All right.
Oh, hi. Sorry, can you go back to the previous slide?
Mm-hmm.
Okay, so you were saying that if I have different pairs of modes, meaning different pairs of vibration and photon modes, right? But then, so I guess I have a naive question, like, how do you make sure that, light is big, the vibrations that you're saying are localized in each diamond unit cell are small? Why do I expect that the light only addresses a single unit cell?
Yes. Okay. Yeah, very good point. So sorry, then I was not clear with that. So I gave you this picture to start with a unit cell, but in fact, you're completely right. So the signal or the vibrational mode that we address is a collective mode. So it's a coherent vibration of many unit cells as a single oscillator, basically.
But you say that there is very little dispersion, so I would expect you would also be addressing modes in other unit cells. So then you would basically, a single photon would be addressing many modes, vibrational modes. What's wrong with my thinking?
So it's let's say it's the spot size indeed covers billions of unit cells. So when you detect a Stokes photon in your detector, there is no information available on which unit cell was excited. Yes. So one way to think about it is that you have to describe the state that you create as a symmetrized the sum of all possible, a bit like a decay state where there is one excitation, but you don't know in which unit cell, so it creates a collective vibration.
But I would imagine that would decay really quickly in room temperature.
Yeah, so you will see it's a time scale, but it's decaying within a few picoseconds.
I see. Okay, so basically I should just think about it as a collective mode a decay mode, superradiant mode, and then I'm getting the pairs. So when you say the n pairs of modes, that just means I am not addressing. I guess my confusion is where in the signal will I see information of one photon mode coupling to many vibrational modes? How does that degrade the signal in the G2 signal?
Yeah, so we expect, so one way you can do that, and we did this experiment, which I don't show here, but you can just replace a single mode fiber by a multi-mode fiber. And then you will be collecting, it's more correct if you think in terms of maybe a case space. So if you can think in terms of the dispersion of this optical phonon in case space. So you have many possible k vector for these optical phonons, and by using a single mode fiber, you select a Gaussian distribution of k vector, which single out a well-defined spatial mode. If you replace this by a multi-mode fiber, you will start to collect Stokes photons, which have many different, which corresponds to many different spatial modes, and then we see this G2 drops to 1.
I see. So basically, the phase matching really helps you choose one single.
Yes. So I think you can think in terms of phase matching in this case because it's a bulk material, and we are in a forward direction. So indeed, that's how it is.
Thank you very much.
Yeah.
Okay. Yeah, we have one more question.
Yes.
Yes. So my question is kind of a continuation of Joel's question. So basically, what you're exciting in the crystal is a phonon.
Yes.
And that's a collective excitation, obviously.
Yes.
But the question is, do you imagine that all these billion unit cells that sustain a single phonon, they are all coherent with each other, or are there different regions in the crystal that have different coherence phase and they are not coherent altogether? And then you will get different, are these the different spatial directions that you would get, basically?
Yes, exactly. So this is indeed, so in the time domain, this is what will happen as well. And it's very difficult to distinguish. I don't think I have an experiment to show you that can distinguish this dephasing of between unit cells from energy relaxation of the collective mode. It's still an open question to me.
Well, energy relaxation is a form of dephasing as well. So.
Yes, so it's probably not so easy to distinguish. Yeah, but maybe there could be a measurement to distinguish. But yes, indeed. So if you have dephasing between unit cells, this signal will decay because you will lose the spatial coherence that is, characterizing this collective mode.
Yeah, and the other question that I have: what would happen if you do the same experiment with the CW source?
Well, you would need an extremely fast detector. So you will need a detector with a time resolution that is faster than the coherence time of this collective mode.
I see. Okay.
And
you
then
use
I think,
APDs,
yes,
or I assume?
Sorry?
You use standard APDs.
Yes, but even if we were to use, we also have these superconducting detectors, but nevertheless, you will see the time scales are really picoseconds. And I think the fastest detector you can find are still above 10 picosecond time jitter. So it's still a challenge. But, it's doable. I think it's probably technologically doable to do it with a CW source at some point.
Yeah. Okay, thank you.
Yeah. Okay, so Professor, we actually have a question in the chat.
Yeah.
So do you see it? Or would you like me to
I need to open it.
If you can't see, I can read it to you.
Yes, polarization. That's a good good question indeed. Thank you, Alexandre. So the polarization is indeed well defined. In the case of diamond, so we excite with linear polarization, and the stocks and anti-stock signal are also linearly polarized. And actually, we use this fact in the later on. I will show you in the entanglement experiment. So the signal is indeed also in a single polarization mode.
Okay, so that's it for questions. You may continue, Professor.
Yes, thank you. So now that I think I went a bit slow in the beginning because it's really important to just, that we understand all these basic facts. And then once we have this capability to study the statistics of the stocks and anti-stocks, we can start to look at the dynamics of this collective vibration that we excited. And the very easy experiment to do that, once we have set these things up, is to do a type of pump probe experiment, but using single photon correlation as an observable. So it's also a G2. So we eventually, what we do is a G2 between these two detectors, but it's a G2 between the stocks and anti-stocks field. So it's a cross correlation. And you might know that if you measure cross correlation between two fields, if these fields are classical in the sense that they are statistical mixtures of coherent states, the cross correlation will be bound by a Cauchy-Schwarz inequality, or a type of Cauchy-Schwarz inequality. And if the fields are quantum and there is a single phonon being exchanged, we can violate this Cauchy-Schwarz inequality. So indeed, this is what we see. So this is the experiment. So this dashed line here is a limit due to the Cauchy-Schwarz inequality, which we can compute thanks to these side peaks. So the side peaks, first, maybe I can comment, they are due to the repetition rate of the laser. So these are, sometimes they are called accidental coincidence. So they are just the fact that we can create a Stokes photon and by chance detect an anti-Stokes photon from the thermal background in a later pulse. But this duration here between pulses is much longer than the phonon coherence time. So this peak serves us as a reference, as a normalization to compute the normalized G2. So here the normalized G2, for example, is 60, and this scale is the raw coincidence rate per minute. So we see a very strong correlation because now when we see a Stokes, we created a vibration, so we have much more likelihood to detect an anti-Stokes in the second pulse, and this is what this quantity measures. But now we can play with the delay between pulses, and as the delay is increased, we see two things. We see that the side peaks remain constant, which is expected because I told you they are just a measure of the background, if you want. But the central peak decays, and it decays following the dynamic of this collective phonon mode that we excited. So we can summarize these dynamics here. As you see, it follows a nice exponential decay with a time constant of 4 picoseconds. So the quality factor is close to 1000. Very high QF products for people of the optomechanical background. So it's actually a pretty good oscillator, given that at room temperature, it features a decent Q factor, and because it's close to the ground state, it has a very good coherence time. Basically, it's coherent during its all over its lifetime. And at room temperature, if you can have a very good oscillator with a very long ring down time, but the coherence will be lost very fast because of thermal phonon entering from the environment. So this is not the case here. Okay, so that's characterizing the system. And then we can do something a bit more fun. We can try to play with the statistics of this phonon mode. So I told you that we are, in this picture, I showed you we exchange a single phonon between the two pulses. But can we prove that we have a single phonon and not, a classical or a coherent phonon state being created, for example? So for that, we need to look at the statistics of the vibrational mode, which is created after the Stokes detection. So if we only measure the statistics of the phonon using this anti-Stokes measurement I showed you before, you remember that we find that indeed we are in a thermal state if we just look at our crystal like that at room temperature, and we find a G2 close to 2. Now we do a different experiment, is that we use a signal from the first measurement to condition the second measurement. So we do a post-selection. Okay, so it's called heralding in the language of quantum optics. It's the way you create single photons based on parametric non-conversion. So here you can imagine this is a parametric non-conversion source. We have a herald detector, and then we expect to project the state of the phonon, in this case, the vibration, into a Fock state based on the knowledge of this projective measurement. Now, you might remember that if I measure G2 on a Fock state, I should find 0, because there is much less probability to get a second excited state compared to the square of the probability to get a single phonon. And that's the experiment we performed. So now it's involving a threefold correlation, because we need to compute this G2 conditional on the click of the first detector. And we see that indeed, at short delay, this statistics is getting sub-Poissonian, so well below 1, around 0.1. And our model also predicts this very well, and it's recovering to the thermal state over, again, this typical 5 picosecond time scale. Okay, so I don't know, I was seeing one question, but I'm not sure if it's a good time to take it. Or...
Oh yeah, if you would like to answer it now.
Yeah, maybe it's best to do it quickly.
Okay, so do you see the question?
No, I see there is Q&A. Ah, yes.
Yeah,
what is the non-normalized coincidence count for G2? Non-normalized, so it's really the raw number of coincidences that we measure. This value of 100 here is the things we measure per minute. So you see the signal is, we get about 1 coincidence per second in this experiment. So it's not gigantic. So we have to acquire for several minutes. Okay. Because the readout is relatively inefficient, because the anti-Stokes signal, the anti-Stokes cross-section is not huge, and there are limitations. I don't have time now to enter into it. Okay, and then to conclude this part, I'd like to show you that we can go one step further and go beyond looking at statistics of the field, but also looking at their joint state and at entanglement. So you know that to demonstrate entanglement, you need to prepare a state in which all information is contained into the correlation between two fields, and that each field measured individually is in a thermal state or in a statistical mixture. And we did that using the setting I've presented so far. So we need to create, so we want to probe entanglement of light and vibration. So we need to find a degree of freedom to create a superposition state where the two fields are correlated, but individually they are in a equal probability of being in one or the other mode. And for that, we use time-beam entanglement, because it provides a very simple setup to probe entanglement using Raman scattering. The idea is the following. So here I show you what happens in the experiment I've shown you so far. So we have a first pulse creating a vibration, and then after a short delay, we recollect or read out this vibration using the anti-Stokes scattering. Now we will call this the early time beam, and we will make a copy of these two pulses to create the same process at a very large delay afterwards. So in this case, it will be several nanoseconds, so something like 3 orders of magnitude longer than the coherence time of the phonon. So these are really two independent modes. And the task that we have to solve is to make these two processes indistinguishable eventually, so that we can prepare a state. So if we can erase information in all the other degrees of freedom, as we mentioned, polarization and time and spatial modes and everything else, so that really become indistinguishable, we will be left with a superposition state of this form, which in fact is nothing than one of the Bell states. If you consider that now your qubit is living in this early and late basis. That's why I draw this block sphere here. And to probe or to prove entanglement, we have to make measurements in bases that are rotated around one plane in this sphere. And we can then compute a Bell parameter, like a CHSH parameter, as I will show you. So the way we did that, because the problem is it's very hard to do these measurements and rotate in this time bin basis. So so I don't show, I'll show you later, but there is a setup to create these two pairs of pulses, and they interact with the sample, and then we end up with these stocks and anti-stocks photons that are spaced into time bins. But using the polarization of the Raman signal, we can prepare these two modes in two orthogonal polarization as well. So now there are 2 degrees of freedom that are entangled, if you want, in this process. And then using polarizing beam splitter, we can make sure that this second interferometer erases the time information, so that eventually we end up having a polarization entangled state, which is easy to measure using the standard. Here we use a variable retarder and polarizing cubes. Okay, so with that, we can then compute a parameter that was proposed by these people in the so-called CHSH inequality. And if this parameter is computed using local realistic theory or hidden variable theory, you will always find it below 2. And if it's above, it's violating this Bell inequality, meaning that you violate some of the assumption in this local realistic description. And that's the setup to do it. I will skip it.
Professor, we have another question.
Yeah.
Okay.
Yeah, so perhaps I'm a little bit confused about this experiment. So basically you are looking at the stocks and anti-stocks, but they are separated with a very large time between them, which means that the coherence was lost in the middle. So how come they are still entangled after the coherence was lost? Well, I must be missing something.
Yeah, they are entangled. Yeah, they are entangled. I mean, I think to get started, it's best to think about it as, because if you forget about the time being degree of freedom and you think about spatial, so the theory is exactly the same as if you had either two diamonds or two spots inside the same diamond, two spatial modes that are independent from each other. And the entanglement is generated by the fact that you erase all information about which vibration or which vibrational mode was excited. And thereby, the only knowledge that you have is that if there is a, let's say, if there is a stocks, there must be a phonon, but this phonon is delocalized in these two modes. And now, instead of being two spatial modes, we use a time mode. So the phonon is delocalized in the first or in the early and late time bin. And by erasing this information, we can demonstrate this entanglement. So I mean, I'm not sure if it's helpful what I said, or if it's still
so you basically can have different combinations of time relations between the photons, and that's why they're entangled.
Yeah, different phases in this superposition that we control using the eventually we transform it to polarization degree of freedom. But there is really, it's a really standard type of entanglement, I want to say. It's not something fancy. It's just that indeed, instead of using polarization or two spatial mode, we use time. And then it's more confusing to understand what it means. And I have to say, it's quantum mechanics. It's not intuitive anyway. but entanglement is there, and clearly we can violate the Bell inequalities, and there is a very good match with the theory, but it's not easy to picture what exactly it means. So, because by definition, the setup is done so that there is no information on whether the pair was created in the first time bin or in the second time bin, and therefore, yes, the state is entangled by construction, let's say.
Okay, thank you.
Yes, so thanks for the questions. And yeah, so I just want to conclude by saying that indeed, we find a very strong violation of this Bell inequalities that we measure, which also lasts during a time scale consistent with the phonon dephasing time. Yes, the marginal states are also in a mixture, so everything is consistent with a maximally entangled state. Although, yes, we don't reach the maximum violation because of some technical imperfection. So just a quick overview of what we can do now with molecules. So if we now start with a liquid, so this liquid is CS2, so carbon disulfide, we can do the same type of experiments. So here I first show you the Raman signal of this under a CW excitation. And you see that this liquid is interesting because it shows two nearby peaks. And we are not sure yet, but our interpretation of that is that these are two isotopes of sulfur that gives rise to this slightly redshifted or softened mode here. And here we come back to the experiment where we just do a anti-Stokes correlation. So this is a 2-pulse experiment where we look at the correlation. And you remember for diamond, you were seeing a nice exponential decay. And here, there is something new. So there is first a component which decays very fast, which we attribute to 4-wave mixing. So we have more evidence on that. So that's a novelty, that with molecules, there is also the electronic nonlinearity is larger comparative to the Raman signal. So the experiment, if you want, is more complex to interpret, and there is this fast component. But afterwards, we see that the data are consistent with the fact that we created a single excitation, which is in a superposition of these two vibrational modes, which are each collective modes, because again, we have many molecules inside the spot, but they are at two different frequencies. So the fact is that our laser pulse, the bandwidth of our laser pulse, is broader than this frequency difference. So we expect to see this quantum beating between the two modes, which we can fit up to some points. And okay, the noise is large, but we can very nicely see the first 1 or 2 revivals. So that's something quite fun, let's say, which eventually, if we can increase the visibility, it could also be used as a witness of entanglement between these two vibrational modes. So it's a different type of entanglement now. It's entanglement between two modes at two different frequencies. But the feasibility we have now is not enough to claim that. Okay, so that's a quick conclusion. And given the time, I think I will try to jump fast on the last part, although yeah, we'll see. But just to tell you, yeah.
Yeah, I actually have a question.
Okay. Yeah, sure.
So again, from Joel, go ahead.
Hello, sorry, I do have some naive question again. So, okay, so even in the simplest pump probe that you show at the first, at the beginning, where you measure the G2 due to the Stokes and the anti-Stokes, you say, well, that's a verification that you didn't prepare a coherent vibrational state, but rather say a single quanta of vibration. And my question is, isn't that already guaranteed by the fact that when you measure these photons, you are filtering through frequency? And otherwise, if you had a superposition of different colors, then that would imply that you also have a superposition of different basically you would have a superposition of different vibrational states, and therefore different and therefore a coherent state.
Yeah.
Is it not just like by construction of your experiment?
Yeah, so actually not, because in the case where, I mean, in this case, we are not talking about the distribution in frequency of the phonon, because the phonon frequency, it's well defined, because in if you are addressing an optical phonon, because the k vector of light is very small, you will be talking only to a very small range of k vector in the phonon dispersion, and the frequency will be sharp. So that's why in Raman scattering you see a sharp line.
Maybe I'm thinking about this incorrectly, but then if you really say if your Stokes or anti-Stokes photons, they have a bandwidth, then the leftover vibration will be a coherent wave packet. Is that, would you agree with that statement or not? Because if you prepare, like, say, a superposition of first and second excited vibrational states, then the photons, the Stokes photons that you will be preparing will be also a superposition of two different colors.
I see what you mean in terms of higher order Stokes, like you would have two photon process.
Sure, like, and that happens all the times with large Frank-Condon factors.
Yeah, I see. Okay, yeah.
In fact, that's the picture that.
Yeah, well, I mean, that's a good point. I mean, I think there are two different processes. One is that you can scatter two Stokes photons, and then you effectively get two photons that are at the same wavelengths.
Yeah.
But you can also have an higher order process where you directly excite indeed to the second Fock state, and that you get a photon that has twice the Stokes shift, or a bit less, or a bit more.
Yes, but then but then in that case, I always expect, according to the molecular spectroscopy picture that we normally have, you always expect coherent states to be produced if the Frank-Condon factors are large. So isn't it just by filtering the photon frequency that you are detecting, or selecting the mode that you are choosing, allowing you to say that you get Fock states?
I mean, yes, you get Fock state indeed by construction, in the sense that if you are able to do the measurements, you expect to see Fock states indeed. No, I agree with that. Yes. I think it's the problem is rather, can you measure it? And that's what we address here. Yes.
Sure. And I guess something very quickly, CS2, I mean, I have always been confused about, well, I find your results that you show about how, I mean, you say you prepare this collective vibration across different molecules in the solvent.
Yeah.
And to me, that's kind of strange, because I expect, because these vibrations are pretty much independent of each other, you form a superradiant state, but they are in different environments, and therefore different electronic states. I would expect the decoherence to be like 10 femtoseconds. So how come do you see any signal after 10 femtoseconds, or am I getting?
No, it's 10 picoseconds. It's very long, yeah. Now the coherence is pretty long. I think that the time scale in liquids are still, in my opinion, what matters here is rather like the rotational time scale, because that's the time scale over which this vibrational coherence will be lost. And remember also, maybe that will also clarify a few things. We are always working far from electronic resonances, so we are working in the off resonance Raman scattering. So the light here, the wavelengths we use are well below any excitonic or, let's say, electronic transition in these molecules.
Sure, but then the molecules, I mean, if you think about it from a Born-Oppenheimer surface picture, I mean, you're creating a superposition amongst many thousands of electronic states, because each molecule has different or maybe Maybe I'm confused about that.
No, I don't think the electronic state should play a role because they are all in the ground state.
Yeah, maybe you're right. I see. Oh, that's very
That's
interesting.
why the timescale are much longer.
So then the temperature is this room temperature?
Yes.
Okay. Oh, this is very interesting. Thank you. Okay.
Yeah, excellent. Thanks a lot for the questions. Yeah, so I don't know. Yeah, just cut me, Matthew, when you think we should stop.
Yeah, so we're already at the hour. So I would say if you still have some content left, if you could, quickly go through it in like 5 minutes, and then we'll.
Yeah. Okay. So I want to just show two things, which are more related to the work with nanocavities. So yes, we had a few years ago this idea that we could use optomechanics to describe surface-enhanced Raman scattering. And it gives us a few ideas. The first one, a work also in collaboration with Diego Martin Cano in Spain and with Tobias Kippenberg. We designed a scheme, which is yet a theoretical scheme, but on which we are working in the SOAR consortium toward experimental implementation, to use this molecular vibration as transducer or let's say frequency mixer between the mid-infrared and the visible. So the idea of this proposal is to design some antennas or nanocavities which have a field distribution that is common to the IR domain. So here it's about 10 micron wavelengths, and the optical domain here about 800 nanometer wavelengths. And in this case, we can enhance infrared absorption into specific vibrational modes, which can be chosen to also be Raman active, so that the anti-Stokes process generated by a pump laser will effectively convert this incoming photon into a visible photon, making it easier to detect. So there are interesting theory in that, which is to find what is the efficiency of this process from first principles, like DFT calculations and numerical simulations, and then also using the optomechanical framework and quantum optomechanics to estimate the noise so that we can eventually arrive at some figure of merit like noise equivalent power. And the noise is due to thermal noise first, of course, of the vibrational modes. But then as you increase here the pump power, you see that the noise or the noise equivalent power in black first improves. So it goes down because you increase the efficiency of the process, but then it goes up because you have a process called quantum back action, which is due to the fact that your laser is not only converting through the anti-Stokes process the vibration into visible light, but it's also generating by the spontaneous Stokes process some vibration. So this vibration will then talk back to the anti-Stokes field. So it's a form of noise generated by your laser. And what I want to point out here, these black dots show what happens when you increase the infrared activity of your molecules, which is a variable that is important for vibrational polaritons. And then we see that at some point our model kind of breaks down in the sense that after these points, we are not able to tell you what happens because we enter the strong coupling. So we enter the regime of polariton, and then our theory doesn't work in this regime. So I think it's a nice future work from theoretical point of view to describe this conversion process in the regime of strong coupling, especially because we think that it could be used in the reverse. So it could be used to excite vibrational mode using Stokes process, and then create infrared photons via the polariton state. So I'll skip that. And then the last thing I wanted to show is that by working experimentally on these plasmonic nanogaps, so I'll skip that, which in our case are so-called nanoparticle on mirror. So these are particles of different size and shapes that are sandwiching a layer of molecule, which creates a very strong field enhancement in the gap. We discovered something very unexpected. So first we confirmed that we can see, so these are Raman lines now plotted in the horizontal axis, and in the vertical it's time. And you see that beyond the standard Raman lines from the molecule we have, we see from time to time, and this lasts for several minutes at low temperature, new Raman lines that jiggle synchronously, which are evidence of single molecule signal, which has been observed also by Jeremy Baumberg and others, and named the picocavity event. So there is very little knowledge on exactly of this picocavity form and exactly what they are caused by, and is there also some other mechanism behind. But yeah, we'll skip most of it. Nevertheless, what I want to show is that another process can be studied in this nanocavity is the emission from the gold itself. So the gold is luminescent, and it's been studied from back in the 60s or 70s on bulk gold films, and then it's been studied in plasmonics. And as Novotny and co-workers described in their paper in 2003, most of this work assumed that the band structure and electron dynamics between all the gold samples that are studied were the same. And actually, we discovered that it's this assumption is breaking down if we look luminescence from nanocavities. So now we excite this nanocavity with green light to excite interband transition in gold. And the video here show you two things. So in background, you have the dark field. So the dark field is a way to measure the plasmonic resonance, the spectrum. And in blue, you have the luminescence of gold, which is enhanced by the resonance. So you see some type of Purcell effect. So the emission is stronger at the position of the plasmonic modes. But you see that this emission, if it's measured with 100 millisecond acquisition, is not stable at all. And it's jiggling and flickering and blinking quite strongly. And it's pretty fun to watch. So below, I show also the distribution of these different plasmonic modes. And this is really what we discovered last year and that we now put on the archive. And our conclusion from these studies is that the gold is not static for sure. I mean, it was already evidenced by the picocavity phenomenology, but this apparently can also cause the formation of probably gold nanoclusters, which can explain these very sharp emission peaks that we see, or simply some kind of nanodomains that, modifies the wave vector conservation rules, leading to increased intraband processes or electronic Raman scattering. So that has some implication maybe on hot carrier dynamics, and also it could lead also to some understanding of optical forces causing these events. Okay, so I'm sorry for the time. I just want to thank my group again, the collaborators we have in these different projects, and just if you have more questions, maybe. Thank you so much.
All right, thank you so much, Professor, for a wonderful talk. We still have about 5 minutes for questions, if anyone has any. All right, actually, since we don't have any questions right now, I'd like to ask a question myself. So regarding the first part of your talk, right, I was wondering if you could apply, since this is the polariton chemistry webinars, I was wondering your comment about the potential of using your techniques on studying the relaxation dynamics of polaritons.
That's one of my plans indeed.
And the systems of collective vibrational strong coupling, right, where you have polaritons that can relax into, the
exactly. So I would love to do that. That's precisely one of my interests, and I think there are some opportunities there. There are also some questions of fundamental nature. Is obvious the Raman signal and the Raman cross section and the Raman process itself, is it affected by the fact that you have a strong coupling with an infrared cavity? That's something that, from the theoretical point of view, has been studied without very conclusive evidence, because there was an early report by the group of Thomas Ebbesen finding some huge Raman enhancement in some of this device with vibrational polaritons. But to my knowledge, it's never been really understood or reproduced. So I think there are some fundamental questions there. But applying some pump-probe spectroscopy in this system using our techniques, we also have a laser system going into the mid-infrared, so we can also do resonant excitation of polaritons. But we don't have the samples yet. So if anybody is interested in sending some good samples, we can work on it. We can probably produce also on samples. But right now this is not we are not doing it, but it's definitely something I'm interested in. I'd be happy to collaborate on that topic.
Thank you. Let's see. All right. So if there are no more questions, again, let's thank Professor Galland for a wonderful talk. And now, before we leave, I want to make a final announcement. So I will, maybe let me share my screen, please.
Yes, I need to stop that.
Okay, thank you. And now, okay, so before we leave, I just want to announce the webinar for next week. So again, it's the same time, 9 a.m. Pacific time, Wednesday, November 18th. And there's guest speaker is Dr. Blake Simpkin from U.S. Naval Research Lab, who will be speaking about vibration cavity coupling, modulation of coupling strength, and ground state reaction rates. And remember, please register at this link, and please share this link to others who you may think would be interested. All right, so again, thank you very much, everybody, and see you next week. Bye.
Bye, everybody. Thanks for listening.
All right. Thank you so much again.